my name is Caroline. I am an electrical engineer, and in this video we're going to talk about voltage regulators. This is the first of a few videos on DC to DC voltage regulators, and this video covers the basics. So we'll start out with what is a voltage regulator. We'll move into different topologies, so we'll talk about resistor divider, moving into the resistor plus zener, moving into the linear regulator, and finally talking about the switching regulator, which is where these videos will have most focus, and we'll spend most of our time on this. We'll talk about pulse width modulation as a way to efficiently regulate voltage. We'll talk about the buck regulator and deriving each of the components from scratch. And then we'll take a side step and talk about the inductor and really dig into the inductor as a way to truly understand from an intuitive sense how a switching regulator works. We'll talk about Maxwell's third and fourth equation there. Then we'll come back to the buck regulator and talk about it in steady state. So let's get started. First question, what is a voltage regulator? At a high level, we can think of it simply as a black box So here we have our voltage regulator, and it takes some DC input voltage. We're going to spend our time focusing on DC to DC regulators. So we're going to say our input voltage is DC, so V in, and we output some output voltage, V out. And almost always the output voltage is different from the input voltage. Now some regulators do this better than others, and you'll see as we talk through the topologies, but another objective of regulators is to keep this V out steady when the I out changes and when V in changes. So the easiest way I can think of to take some input voltage V in and get a different output voltage V out is with a resistor divider. So let's draw that. So let's say that we wanted a V in of 4 volts and we wanted a V out of 3 volts. We could accomplish this assuming that there's no current being drawn from the load or from V out with a resistor here of 10 ohm and a resistor here of 30 ohm. And we can see that 1/4 of the voltage is going to be dropped across this 10 ohm resistor, and 3/4 are going to be dropped across this 30 ohm, giving us an input voltage 4, output 3. Now, this is great, but not so great actually. When I out starts to change, let's say that we start drawing more current from V out here, and we can model, or we can say that we're drawing current by adding a resistor here, which will draw current. So if we do that, we'll see that, okay, V out's going to start dropping. So that's not great. And let's say we change V in. Now we change V in to 5 volts. Well, our V out is going to change as well. So yes, we can change the voltage with a resistor divider, but it's not very good at keeping it steady under different I out and V in conditions. Okay, so let's think about another option. Instead of this resistor here, let's turn this into a zener diode. And let's say that we want a V out of 3 volts. We would say that this zener diode has a reverse breakdown voltage of 3 volts. We would select one. Now, ideally, in the textbook form, this zener diode, as long as this voltage here is not below 3 volts, and we reverse bias our zener, the zener will do whatever it needs to do to the current in this circuit to keep this voltage here at its reverse breakdown, which here we have 3 volts. So let's assume no current is coming, let's say no current is coming here, and the zener's reverse is 3 volts. We can have 100 milliamps. The zener will take 100 milliamps, and we will realize our 1 volt drop across this resistor. Now let's say that I out goes to 50 milliamps. So now the Zener will only take 50 milliamps. It will do whatever it needs to do to the current to keep its voltage at 3 volts. And so we'll have 50 milliamps going through the Zener and 50 milliamps going to the load, I out. And we'll still have 100 milliamps going through this 10 ohm resistor for a voltage here of 3 volts. So great. We're already seeing that with different I outs, our current, our output voltage will stay steady. But not so fast. Let's say that all of a sudden our I out changes to 200 milliamps. Now we're going to get a 2 volt drop across this 10 ohm resistor, excluding any Zener diode current. So we've got 200 milliamps going here. Now this leaves us with 2 volts. Now the Zener is no longer reverse biased, so it can't draw current it can't do anything to get its voltage to 3. So we've gone out of regulation and now the voltage is at 2 volts. So this topology has its limitations, and also another thing to note is that if in a lot of consumer electronics, temperature changes, and this reverse breakdown voltage is very temperature dependent, so it will change when the temperature changes. So this is not ideal if we're trying to keep something very steady and we have our reverse breakdown voltage changing all the time when the temperature changes. So let's move on to the next topology. They just keep getting better and better. And we're going to jump into our linear regulator. So now instead of this resistor up here, we're going to insert a FET, and here we're going to use a PMOS. And we are going to operate this PMOS in the linear region. So it's a voltage-controlled resistor, essentially. And this is opposed to the saturation region where we have fully enhanced our channel and our RDS(on) is as low as possible. Here we want to be able to change the resistance on the fly by adjusting this gate voltage. Now, this linear regulator is the first regulator that employs negative feedback, which really means just sensing the output, and if it's not what we want it to be, doing something in the circuit to change it. And we can realize this negative feedback by using an op-amp, operational amplifier. And so what our op-amp will do, if we have negative feedback, which I'm going to implement right here, and we attach a reference voltage here of, let's say, 3 volts, it will do whatever it needs to do to its output terminal here to get the negative and positive terminals to be the same voltage. So if we want our V out to be 3 volts in all circumstances, then we attach a 3 volts on this terminal, and now this output voltage will do whatever it needs to do to keep this terminal equal to this terminal equal to 3 volts, which is what we want. And here we're attaching the output of our op-amp to the gate of the PMOS so that we can change its resistance on the fly to accomplish that. So for an example, if our voltage all of a sudden drops, let's say we're regulating at 3 volts and all of a sudden our I out increases and so our voltage droops down to 2.5, the op-amp is going to sense, hey, my negative input is less than my positive input, so I need to drop my output voltage, which will drop the output voltage at the gate, which will lower the resistance, and now the voltage drop across this FET will be less, meaning that our output is going to go up. So at a high level, that's how the LDO works. And when I said LDO, a lot of times people call linear regulators LDOs, and an LDO is a type of linear regulator, and it stands for low drop out, which means that we can get this voltage here to be not much higher than this voltage here, which means we can get the resistance across this FET to be pretty low. So a couple caveats about this drawing, it's simplified. The first thing is that we don't normally hook the output of the op-amp directly up to the gate of a MOSFET. We usually have some gate drive stage in here. We also usually employ some sort of input capacitance for high frequency filtering and some output capacitance here which I'll talk about in some other videos. And normally these reference voltages here are not as high as 3 volts. We see them often around 0.6. And so we need to scale this negative terminal so that when the output equals 3 volts, the voltage here is 0.6. So you'll often see resistors here on the feedback trace sized so that when the output is 3 volts, this voltage here equals 0.6 volts. So we'll try to make these two voltages the same, both 0.6 volts, which means this voltage will be 3. So let's talk about efficiency and power here. So all of the voltage regulators that you've seen so far have accomplished this regulation of voltage, or changing the input voltage from the output to the output voltage, by what we call a series pass element. And it's a resistive element, either a resistor or a FET that thinks it's a resistor, in between the input and the output, our series pass element. So we know that P equals I times V. So when we have a current across this resistive element and a voltage, we are taking electrical energy and transferring it into heat. So we have a power loss here, which generally we don't like. Now, if you have a low current or a kind of a low voltage between the input and the output, this is generally acceptable, and it's something that we're willing to sacrifice. But if we're more concerned about heat and power loss and efficiency, or we have high currents, or we have a big voltage differential between our input and our output, this becomes a concern. So we need to think of a more efficient way to regulate our voltage. And that brings us into switching regulators. The reason that we are losing power in these topologies is because we have resistive elements. If we were to remove all of our resistive elements, we would not be wasting power due to heat. So let's think of other ways we can, or another way that we could take an input voltage and get a different output voltage without using resistive elements. And now I'm going to introduce the term PWM, pulse width modulation. So let's say this is time and this is voltage. Now, let's say we want to accomplish the task of taking a 4-volt rail and somehow obtaining a 3-volt rail from it. So let's say that we have some way where we can take in 4 volts, our input, for 3/4 of the time, and then not take anything in. And then take in 4 volts for 3/4 of the time, and then not take anything in, and just keep repeating that. Now this waveform doesn't look like a very useful waveform as a voltage rail. We want them to be steady, and this doesn't look like something we would want to pass down to an IC to power a chip. However, what if we took the low frequency content of this waveform, or we low pass filtered it, or we took the DC, or the low frequency, or the average. What that is, if we take the DC component of this, or the average, that gives us 3 volts. If we're at 4 volts for 75% of the time and 0 volts for 25% of the time, the average of that is 3. And now this is a waveform that looks like we could send down to an IC. So let's say that we wanted, instead of 3 volts out, we wanted 2 volts out. So what we would do then is only take in 4 volts for 50% of the time. And now the new average value if we're at 4 volts for 50% of the time and 0 volts for 50% of the time, is 2 volts. And so what we can do is we can change the amount of time that we're taking in the input voltage, the percentage of time, to adjust our average value, which will turn into our output voltage. And we call this pulse width modulation. So if we're on for